In this video, we are going to explore the generator effect, which is also commonly referred to as electromagnetic induction. To begin understanding this fascinating concept, let us first imagine we have two magnets positioned with a magnetic field established between them. Now, if we take a piece of wire that has been carefully bent into a coiled shape and we move this wire through the magnetic field, a potential difference will be induced within the wire. This can be visualized by the appearance of positive and negative signs at either end of the wire, indicating the buildup of electrical charge. There are some very important details to consider at this point. One of the key things to notice is that whenever the wire stops moving, such as when it reaches the top or bottom of its movement path, the potential difference disappears. This occurs because it is not just the presence of a magnetic field that matters, but specifically the change in the magnetic field that the wire experiences as it moves through it. This change is what actually causes the potential difference to be created. Therefore, if the wire is not in motion, then there is no change in its magnetic environment, and as a result, no potential difference is generated. Another important observation is that the direction of the potential difference reverses each time we reverse the direction in which the wire is moving. This explains why the positive and negative signs continue to switch sides whenever the movement changes direction. At this point, we only have a piece of wire and not a complete electrical circuit, so even though a potential difference is induced, no current is able to flow because the electrons do not have a full loop to travel around. However, if we connect the two ends of the wire together to form a complete circuit, then the induced potential difference will cause a current to flow, as the electrons now have a continuous path through which they can move. Interestingly, the same effect can be achieved if we keep the wire completely stationary and instead move the magnets up and down. In this scenario, the wire still experiences a changing magnetic field, which once again is the essential idea behind electromagnetic induction. On the other hand, if we move the wire back and forth in a direction that does not actually alter its position within the magnetic field, no potential difference or current will be generated because the magnetic environment surrounding the wire remains unchanged. Now, suppose we want to increase the magnitude of the induced potential difference and the resulting current. In that case, there are three main strategies we can use. The first method is to increase the strength of the magnetic field. For example, by using magnets that are stronger and produce a more intense magnetic field, we can induce a greater potential difference. The second method is to increase the speed at which either the wire or the magnets move. A faster motion leads to a faster change in the magnetic field, which in turn causes a larger potential difference to be generated. The third strategy involves shaping the wire into a proper coil with multiple loops or turns. The more turns the coil has, the larger the induced potential difference becomes, because each loop contributes to the total effect. To summarize everything we have covered so far, when a wire is subjected to a changing magnetic field, a potential difference is induced across it. If the ends of the wire are connected so that there is a closed circuit, this potential difference will cause a current to flow around the circuit. Additionally, we can make this induced current stronger by increasing the magnetic field strength, moving the wire or magnets more quickly, or by adding more turns to the coil. Finally, we learn how this same concept applies when we insert a single magnet into and out of a coil of wire. As the magnet moves relative to the coil, the magnetic field experienced by the wire changes, which induces a potential difference. And since the coil forms a complete circuit, this results in a flowing current. Just as before, reversing the direction in which the magnet is moved also reverses the direction of the current. Similarly, if we flip the magnet around to swap its poles, we also reverse the direction of the current. That concludes everything for this video. I hope all of this information was clear and helpful, and I look forward to seeing you again very soon.